Hello, everyone. This is Dennis. Welcome to my presentation on homework number 7. So, some steps for the completion of homework number 7. First and foremost, we have to take our homework 5 and add a time-dependent solution for it. So we have to combine homework 5 with time dependency. We have to prompt the user for input values as shown in number 2. We have to add a concentrated heat source at a user input time, location, and have the user input a magnitude for that heat source as well. We have to be able to avoid numerical oscillations and find physically realistic solutions by selecting appropriate parameters. We have to also explain our profile and what we expected to get. And finally, we have to answer the all-important question, is it possible to replicate the steady state solution using our time-dependent one? So let's start with time dependency plus homework number 5. So we are taking homework number 5's get FEA solution and adding all of the variables that we need. For example, we need a capacitance matrix for this time-dependent solution, and we have to also make it a global capacitance matrix using either consistent formulation or lumped formulation. For the most part, the loop stays exactly the same. The only thing we're actually adding is a global combination of our C matrix, which is just the same as K, and then adding the CE that we choose, either lumped or consistent formulation. Furthermore, we have to reduce our capacitance matrix in the same way that we reduced our stiffness matrix K, which you can see right here highlighted in blue. The only thing we add in that's a constant is the lambda value, which is used to calculate the time-dependent solution. Next up, we have the user inputs. First and foremost, we have to ask the user how many nodes they would like their time-dependent heat simulation to have, which is located in homework 5's get input values under NN. Next up, we have to ask the user which type of capacitance formulation they'd like to have, either consistent or lumped. In order to make sure the user can only pick one or the other, one being consistent and two meaning lumped, we stick it in a while loop with a few if statements, making sure that the capacitance choice that they pick is either a 1 or a 2. Next up, we have to ask them what they want the initial temperature throughout the bar to be. This is the initial temperature at time equals 0, and it will be spread out evenly throughout the bar. Furthermore, we have to ask them what they want the temperature at the end of the bar to be, T of H. Next up, for important time variables, we have to ask them about the delta time step increment, the time step that they would like the solution to run in, and the total time they'd like this simulation to last. We give them a note to make sure they know that if the delta time increment is too large, they should expect oscillations. Next up, we have to ask them about the FDM parameter, theta, where 0 is a forward method, half is central, 2/3 is Galerkin, and 1 is BWD. In order to make sure that they pick a value that we like, we can stick their input within a while loop, similar to the capacitance choice. Next up, we have to ask them about the concentrated heat source, what magnitude it should be, where along the bar it should be, its X location, and at what time they would like this point heat source to occur. Note, we have to make sure the time they pick to apply the concentrated heat source is less than the total time that the simulation takes. Otherwise, it's invalid. In order to check to make sure that they have input correct values, we can place each value that they need for the concentrated point heat source within a while loop. If they choose a time outside of the time that we've specified, ergo, if the point heat time is greater than the total time, then we will let them know that the value they entered is invalid. Similarly, if the X location they picked is not within the bounds of 0 and the length of the bar H, then they have also picked an invalid value, and they must try again. In order to add a point heat source at a specific time designated by the user, we must make sure that it's less than or equal to time and have a dummy counter so that it's only added once into the F matrix instead of iteratively. In order to find out which element location it is, we take the X location that they've designated and divide it by the element length. We round that value and then we add 1. For example, if the user wanted to have it at 0.5 meters with an element length of 0.1, this would place the X location within the 5th element. And then after adding 1, you would find out that it was at node 6. And now we must make sure that the time-dependent solution we get from our MATLAB code is physically realistic and does not contain any numerical oscillations. In order to accomplish this, we can set time step constraints for whichever capacitance method they choose, either lumped or consistent. As far as the values that we chose for our problem, we have lambda equals to 12, LE or element length equal to 0.04 meters. We've chosen a Galerkin's method, which is theta equals 2/3, and D equal to area max, where area max is the maximum area that exists within the structure. Our structure contains 4 distinct section moduli, and the maximum of those values is 0.08 meters squared. We choose the maximum area because it minimizes the expression above and helps us find the smallest time step. We want to make sure that we are below that time step for each one of these expressions. And as you can see from this formulation below, our time step of 0.02 fits all the criterion. And finally, our expected profile. The expected profile we want to have is the steady state solution for homework 5, which is similar to this one right here. The right bound is at TH, which in this case was 100 degrees Celsius. It steadily rises up and then tapers off towards the beginning of the bar. Finally, in order to maintain a consistent solution, we have to add back in the temperature at node H, since we reduced our matrices earlier. We do this for phi B and phi A, the time at B and the time at A. Here we have our simulation. It looks like it is going towards our steady state simulation. Let's watch and observe what happens. At time equals 5, we can see that our solution is headed towards steady state. We have a sharp linear increase at the very right side of the bar. As we can see here, as time moves forward, our solution goes towards steady state. The right side of our graph follows a linear pattern, while the left side of our graph seems to be tapering inwards. Our graph almost looks exactly like our steady state solution now. Our left side of the bar is beginning to taper off, and the right side of our bar is linear, similarly to our steady state solution. As we can see, our simulation has gone on for approximately 27 seconds. Our temperatures are not changing by a lot at this point in time, and our solution is approaching steady state. Once the values stop changing completely, we will have known that our solution has reached steady state. However, as you can see, it models almost exactly as our steady state solution. The left side is completely tapered, followed by a parabolic decrease, and finally a linear decrease all the way down to 100 degrees Celsius, which is fixed at T sub H. Finally, it looks like our solution model is not changing by a lot. So we can assume that we've achieved steady state. And indeed, it is our steady state solution, similar to the graph we got in homework 5.